Hello and welcome back to our case study. So in this case study we want to apply our skills in a bit larger case actually, and we will apply random number generation, vectorized operations and the so-called method chaining. And also we want to compare the Numpy and the Python standard library in terms of performance, length of code, readability, and actually how intuitive the respective code might be for others. So, but now let's start and let's assume the following situation. So we want to create 100 random integers between 1 and 10. And then we want to count how many times we get the integer 1. So on average, I would expect 10 times out of 100. And if we do this only one time, the simulation, the result can be quite different to what we expect. And to check if our expectation that we get 10 times the integer 1, we have to simulate this many times. So let's say 10,000 times to get a statistically reliable result. And then we simulate 10,000 times and then we calculate the mean of all outcomes or all simulations. And then we should be very close to 10 on average. At least I hope actually. Alright, so let's start and we import Numpy. And this is already the whole Numpy code, but I would like to derive the code. So first of all, we want to create 100 random integers in the range 1 till 11. So we get here 100 integers. And then we check which of them are equal to 1. So then we should get a ND array with Boolean objects. So here you can see false, true, false, false. And then we want to calculate how many times we have the integer 1, and therefore we just sum up our array. So let's remember that a true stands for the value 1 and a false stands for the value 0. So if we sum up here the Boolean array, we should get the number of occurrences of the integer 1. And here we have 12. So our expectation was 10, and here only with one simulation, because it's random, we get 12. And now let's repeat this process 10,000 times. So we create 10,000 times 100 random integers. So in total 1 million integers, and then we reshape these 1 million integers to a matrix of 10,000 rows and 100 columns. Then for each integer we check whether it's equal to 1 or not, and then we have to sum over all rows how many truths or how many times we have the occurrence of the integer 1. So we have to take axis, so equals 1. So we sum over each row. We have 10,000 simulations. Now, and if we execute this here, there we can see now we get 10,000 results. So we simulated this process 10,000 times. And in our first simulation we got 12 times the integer 1, and the second one 9 times, and we also get 6 times, 4 times, so there's much statistical variability here actually. And if we want to check whether our expectation is true, that we on average expect 10 occurrences of the integer 1, we have to take the mean of all results. And there you can see we are very close to 10. So now here we created many random numbers. We used the vectorized operations and also the so-called method chaining. So we changed one method after another. So we started to create a random integer, then we reshaped it, then we took the sum of all truths for each row, and then we took the mean of all results. So this is called method chaining. And we can also measure the time that this process or this code takes on average with the time function. It takes a bit of time, so we have 1 million random integers. So we got here 60 milliseconds, and now what we want to do now, we actually want to simulate the same process with the Python standard library, and therefore we have to import the random module. And here's actually the code that does the same job as here our Numpy code with Python standard library instruments. So let's start here with the inner for loop. So 100 times we are creating a random integer in the range between 1 and 10, and then we check for each created random integer if it's equal to 1. And if it's 1, we append a true to our list L, and if it's not equal to 1, we append a false to our list L. And then we calculate the sum of all of our truths and false in our list L and append this to a results list. And in the result lists are all results for in total 10,000 simulations. I put this whole code here into a function called simulation, so that makes it easier later here to measure the time actually. So there's no deeper reason for it. So we can execute the cell here. And then we can run our function and simulate with Python standard library. And there you can see we got 9.9. Also here we are very close to 10. And now let's measure the time or the performance of the code and compare it to Numpy. We have here 1.2 seconds, so this code took us 1.2 seconds, and Numpy did actually the same job in 16 milliseconds. So Numpy is 100 times faster, and that's actually a huge difference. And you can also see here we have a very condensed code, so we have actually only one line of code here. And in contrast with the Python standard library, we have here a nested for loop and if statements. However, some people say that here the readability of the code is much easier, and also it's more intuitive to understand. So at least if you have done 2 or 3 times a nested loop and some if statements, it might be quite easy to understand what the code is doing here. In comparison, the vectorized Numpy code and method chaining might be a bit less intuitive, at least if you are not used to it. Alright, so this is it for the time being, and in the next session we will have a look at summary statistics. So hope to see you there. Bye.